Okay, question 12, we're looking at a Bernoulli distribution, and then we're looking to apply our knowledge of the distribution of a binomial distribution and then a normal distribution. So first of all, looking at the initial problem, I know it's a Bernoulli problem or a Bernoulli trial because we either have orders being being shipped within 54 hours or they're not shipped within 54 hours. They're the only two outcomes that I'm concerned with. We know the probability of a success, where a success is that it is shipped within the given time frame. That probability is 0.9, so the probability of failure is 0.1. In this particular question, we have 150 items that are being shipped. So we've got 150 repetitions of this Bernoulli trial. So our value for n is going to be 150. In part 1, we've got 135 pieces being shipped within the given time. So to find the probability that we have exactly 135 successes, we need to use our combinatorics. So in order to have exactly 135 successes, it means we must have 15 failures. So one way of determining the probability of getting 135 successes is doing the product here, probability of success 135 times, multiply the probability of failure on 15 of those times. And then we've got the number of ways that can be done, which is 150 C 135. And you can do the calculations yourself. With part 2, we now need to look at the distribution of these results once we start looking at the binomial distribution. Now, at the first point, we need to show two things. One is that the expected value is 0.9, and then we need to work with our standard deviation. So the expected value of any discrete probability distribution, we'd multiply the probability of a given outcome by that particular outcome, and then we find the sum of all of those values. So with a Bernoulli trial, we would denote the probability of success is 0.9, and we denote the actual value for that of 1. It occurs, so we'll say it occurs, we'll assign a value of 1. If we have a failure, that means that the success doesn't happen, so we assign it a numerical value of 0. By doing that, we can now find the sum of the products of the probabilities and their particular outcomes. And what you'll find is that you end up with your expected value of the distribution is the same as the probability of a success. For the standard deviation of the sampling proportion, you would need to think about, well, how do we find the standard deviation of a Bernoulli distribution? Now, we have a formula to find the standard deviation for a Bernoulli distribution. It's the square root of NPQ. Now, in this particular case, if we consider just having one trial, we would then divide that by the number of trials that we've had. Now, another way to express that is going to be the square root of NPQ. I'm going to write it like this, square root of n times the square root of PQ, and dividing that by n. This part here, root n over n, is the same as 1 over root n. So now I can say, well, this is going to be the same as square root of PQ all over n, where the n we can bring inside the square root. So either this version or this version down here are perfectly fine to use. The one I've taught is the one on the left-hand side, which is why you can see that written there. Okay, so substituting in our value for P, Q, and N, we can get the required standard deviation of the sampling proportion. Okay, part 3, and this is the one that you've asked about. This is actually an advanced question now, where we use the standard deviation of our sampling proportion, and we use our expected mean, or expected value, of our sample proportion. Other than that, this is an advanced problem and an understanding of the symmetry of a normal distribution. Okay, so the information that we're given in the question, I've summarised over here. We've been told that the probability that we get at least a particular number of items arrived or shipped within the given time, the probability of that was 90.15%. So whatever this particular number of items is, we're saying that the probability of getting that number or any more items than that distributed within the given time, the probability of that occurring is 90.15. Now, let's go back and have a look at how to interpret the table here. When we're interpreting our table of values for our normal distributions and our probabilities, you notice that the z-scores we're working with are positive, and this is almost always the case when you're presented with this information. And the way you interpret this is if we look at one particular cell in the table, if we look at, say, this one here, the way to interpret this is the probability that the z-score is less than or equal to 1.14. That probability is 87.29%. Obviously rounded that to 2 decimal places. So this table allows us to work out the probability that the z-scores are less than or equal to a particular value. But this question is asking us about this cutoff point where the probability the score is greater than that value is 90.15%. So it's the other way around. So we need to use properties of the symmetry of a normal distribution. So we've been asked to do something like what's in this first diagram. The probability the score is greater than a particular value, in this case a particular z-score. But in actual fact, by using the symmetry of our normal distribution, that's the same as finding the probability that a score is less than the opposite sign of that z-score. So if you change the sign on the z-score and you change your probability from being greater than to less than that new z-score, you'll find those probabilities are the same. And this is the type of value that we can read from our table. This one we can't. So we need to use that symmetry there. So putting that into some mathematical stuff that we can use. Excuse me. Our questions ask us to find, now we'll say Z here, but we then need to find the actual number that corresponds to that Z-score. The question's asking us to find the probability that Z is greater than a particular Z-score. Sorry about the X's in there. Now, if we change the sign on that Z-score, so here I've got a positive, over here I had a negative, doesn't matter if we switch them around. If we change the sign on our Z-score, we can change the direction for our probability. So we're going from wanting scores that were greater than a specific value over here, we now want the scores that are less than, and then we change the sign on that value. And this is the value that we can read from a table. So what we need to do now is go back to our table and look at which value in our table, or which Z-score in our table, corresponds to a probability of 90.15%. Well, the only value in the table that's close to that is this one here. That's the closest that we have. If we round that off to 4 decimal places, we've got 0.9015, which is equivalent to what we're being asked about. So let's go and use that information. So the probability that Z is less than or equal to 1.29 gives us our required probability. So from the table, the probability that Z is less than or equal to 1.29 is approximately the value we were requiring. So therefore, if I change the direction of the sign and I change the sign on the Z-score, the probabilities are going to be equivalent. So that's also going to be 0.915. So that's saying that the probability of getting any z-score that's greater than or equal to this value is the required probability. So all we need to do now is we need to find the actual score that corresponds to that z-score. So the actual score, the number of items that's going to be our minimum value here, it's going to be our cutoff point, we can use a z-score of negative 1.29. We can use our expected value for the mean, and that was our probability 0.9. And then we've got a z-score of negative 1.29 means that we're 1.29 lots of the standard deviation below the mean. So we've got 1.29 lots of the standard deviation, where the standard deviation is going to be the standard deviation for our sample proportion, which we did in part 2. Now, something you'll notice here. With this z-score here, the calculations we've done here is for one trial. But we've got 150 trials, remember, so we're going to multiply this by 150. Which is then, you can do your calculation, and we end up with n being 130. So the probability that we have at least 130 boxes delivered or shipped within the given time is 90.15%.